Welcome to lecture 12 of Machine Learning from Data, Regularization. Now this is a tool to combat overfitting, so it's important. And what's overfitting? We discussed this last time. It's fitting the data more than is warranted. And here's a classic example of overfitting. You have this blue target function, a few data points generated with some noise, and you throw at it a reasonably complex hypothesis set, and you fit, and you get this red curve, which is nonsense. Okay? So we drilled down. What causes that red curve, which is nonsense? Okay? And we identified noise as the primary cause of this overfitting. Okay? And what is noise? Noise is the part of the y value you cannot model. But this y value is present in the data, so even though you cannot model it, you try to model it and are led astray, and this hurts the learning. Okay. Now there are two kinds of noise. The first is what we are very familiar with, these random measurement errors as illustrated by this garbled picture of the elephant, and we call this stochastic noise. It's no surprise that if you have these random measurement errors, it's going to lead learning astray. The interesting case is deterministic noise. Okay. Now deterministic noise is coming from an overly complex target function. A target function which is more complex than the capabilities of the learner, the hypothesis set. Okay, so this means that the target function has nuances and complexities that cannot be modeled. These nuances are present in the data. The learner tries to model those nuances and gets led astray, and that hurts the learning. So stochastic and deterministic noise, you try to model them, but you can't model them, and that hurts the learning. Now, this deterministic noise is illustrated, nicely by this picture of the elephant, which appears in the, 3-year-old's picture book, where, we try to remove the nuances and complexities in presenting the data to the 3-year-old, because it's easier to learn when the nuances and complexities that you cannot model have been removed. So we're trying to remove this deterministic noise in order to help the 3-year-old. Humans, tend to be very good at, extracting the simple pattern, finding the basic idea, ignoring the noise and the complications. But imagine showing this, this picture of this garbled elephant to a computer. It's going to pay equal amount of attention to all the pixels. So it needs help to simplify. It can't do it automatically. Now, one way to help is to extract good features, summarizing the essential relevant information. And that happens before learning. Now, once you have got your good features, setting a good baseline for E in and E out, as you're learning, now at some point you start fitting the noise, you start overfitting, and that's where regularization can help. During the learning, when you start fitting the noise, you can apply the brakes. Okay, so that essentially, in a nutshell, is regularization. Regularization is this cure that, this cure that prevents the tendency to fit the noise, to get distracted and be led astray. Okay, so, and by preventing you from fitting the noise, you improve the out-of-sample error. Okay, so how does it work? Basically, the idea is, in order to prevent you from fitting the noise, we have to constrain you somehow. Okay? And that way, you cannot fit the noise. But if we constrain you somehow, maybe you cannot fit the target function. Okay? So that would be a side effect of this cure, regularization. And we must make sure that the side effect doesn't, overpower the actual benefits. Okay? The benefit being you don't fit the noise. The side effect is you might not fit the target function. You might not fit the signal. Now, regularization, we are to some extent familiar with it, although we may not have looked at it as regularization. So think, the young child who's got this complex neural network trying to represent reality, and all around you is all this complexity and randomness, and you can go this way and that way, and you'll get totally led astray by all the complexity that's out there. And then your parents and mentors and all the people who influence you come along, and they constrain you, they focus you on basic principles and bring you up. So in some sense, we're all regularized by our parents. Otherwise, we would go on and overfit all the complexity and all the randomness that's out there. Okay? So it's a good thing that, the parents came along during our learning, regularized us so that, we have a better out-of-sample outcome. So we're all regularized by our parents. Now, when it comes to the machine, okay, we need to make sure that, the regularization, while constraining the model, doesn't have too much of a side effect. So let me show you in a very simplified setting, the potential benefits of constraining the learner. Okay, and here's an example that we saw before, okay, when we talked about bias and variance. So, you have a target function in blue, and we generate data sets, and, you produce this wild assortment of linear fits, okay, completely wild. Okay. And what would it mean to constrain the learner? So, for example, we might say, you're not allowed to fit with huge slope. Even if the data warrants a huge slope, you must do the best you can with small slopes. So let's say we constrain the weights. The slope is one of the weights. So let's say we constrain the weights to be smaller. Look at what happens. It significantly reduces the wildness in the fits. Okay. Now, the question is, does it work? So let's see who the winner is. Okay. So on the left, if we repeat many times, on average you get this red fit. And the wildness, the variance in the fit is captured by this gray region. Okay. And on the right, the constrained, the smaller weights fit. We'll call this the regularized fit curve. I'm constraining the learner. You get almost the same red curve on average. So on average, you're almost fitting the same, but look at the variance, the gray region. The wildness is significantly reduced. Okay. And, so when you look at the numbers, and we saw this before, the bias is 0.21 for the case of lines with slope. And when you constrain, okay, it hurts you a little bit. The bias goes up to 0.23. So that's the side effect of this constraint, this regularization. Here's where we gain big time, okay? And it's the gray region. The variance drops from 1.69 to 0.33. The variance drop is huge, more than warranting the side effect. So we have sort of significantly decreased the variance at the price. The cost is a small price that we pay in the bias, the side effect. And we had this decomposition of the out of sample error. It's the sum of the bias and the variance, and so the bias and the variance with the regularized fit is much better. Okay. So the constrained regularized fit is much better in this example. And now I'm going to remind you, we also studied the constant model, okay, when we compared this line with slope with just the flat lines. And the constant model had a bias of 0.5 and a variance of 0.25. So the sum is 0.75. So the regularized fit even beats the constant model. So it turns out to be better to have the extra flexibility of the lines with slope as opposed to just the flat lines. So it turns out better to have this extra flexibility of the lines with slope. It turns out to be better off to have a complex neural network in your brain. Okay? But if you just let it go wild, you're in this world of no regularization, and then it ends up being much worse. Okay? But if you have this extra flexibility, but you have a way to systematically, rein in the fitting power, to systematically apply the brakes, to systematically regularize, then you can beat the simpler model. Okay? So the complex model with the ability to brake is better than the simple model with full capability. But the complex model without the ability to brake is a disaster. And that's that red fit, that total disaster that we saw at the beginning. So, okay. So, now we're going to discuss the mathematics. It's going to get a little bit dense. We have to, we have to figure out how to mathematically implement regularization in some of our favorite machine learning models. And so, we'll derive regularization, from starting from some concept similar to the VC theory. Okay, and at the end, we're going to derive this very popular method of regularizing called weight decay, and then we'll see some experiments and some results. Okay. So let's move to the board. Okay, fasten your mathematical seatbelts. We've got some intense derivations ahead of us, but, don't panic. I'll give you a quick overview. So starting with, we'll start with a high-level view of what we're trying to accomplish, okay? And then we'll focus in on the concrete linear model, specifically linear regression. That's going to be mathematically the easiest to sort of expose the ideas, okay? And then actually get a working algorithm. And one goal is to show you how, this example that we saw where we constrained the fit to have small slope, lower weights, show how that helps. Okay, so link constraining the model to better generalization. Okay, and that's going to lead us to the hard order constraint and then the much more mathematically convenient soft order constraint. Okay, and so then within this soft order constraint world, we're going to do the mathematics for the linear model and actually develop the algorithm. And it's going to be very similar to the pseudo-inverse algorithm. So we will have a very concrete model, the linear model, okay, the regression model, which is actually quite powerful because we have, nonlinear transforms which can take us to arbitrarily complex spaces. Okay, so we have this concrete model, and then we will have the concrete mathematics and the algorithm developed within that setting, and it's nice and clean, and we can see exactly what's going on. And we will develop, this very popular form of regularization called weight decay. And then, that doesn't, now we're not going to be prevented from using this weight decay technology whenever we do machine learning and similar constraints, okay, with this sort of, clean mathematical derivation as sort of the reasoning for why we use regularization. Okay, so let's begin. Okay, so at a high level, what are we planning to do? So I'm going to remind you of the VC inequality. So E out of G is at most E in of G plus omega, so an error bar. But what did this error bar depend on? It depended on the hypothesis set. Okay, so on what's it saying? What it's saying is that if you can get a comparable error in sample, using a simpler hypothesis set, then you expect the out-of-sample error to be better. So fitting with simple H is better. Okay, and now, what our plan is to sort of take this a step further. So that's what regularization does. It takes this a step further and says, well, if it's better to fit with a simpler hypothesis set, then maybe it's also better to fit with a simpler hypothesis. So we're going to try to replace this with, some error measure, some error bound, some error bar, let's say, heuristically, that says that if you can get the same in-sample error with a simpler hypothesis, then you are expecting a better out-of-sample error. Okay, so we're going to try to replace this with something like an omega, an error bar that depends on G, and sort of quantifies the complexity of the hypothesis. So replace the error bar, which depends on the hypothesis set, with an error bar, not quite a rigorous error bar, but some quantity that behaves like an error bar that depends on the hypothesis, measuring its complexity, penalizing you for a more complex hypothesis. Okay. And there are several questions, does it work? And, so first of all, does it work? And second of all, how do you measure the complexity? And third of all, how do you even implement such things? Okay. So that's, part of what we're going to describe today.